In physics, we usually come across two kinds of quantities, scalars and vectors. Time, mass, energy, speed, volume, and density are some scalars to be mentioned, and force, velocity, acceleration, and momentum are some famous vectors. But what is the difference between, for example, the velocity and the speed of a ball? When we use the term velocity, we are referring to a magnitude and a direction, while a speed is just a magnitude, a number, and doesn't have a direction. We illustrate vectors using arrows. For example, this ball is moving at the speed of v, and its direction is shown as you can see. We can add two vectors and get a new one. Adding vectors is associative, meaning that it doesn't matter if we first add the two first ones or the last two ones. To subtract a vector, what we need to do is adding the opposites. What happens to the addition of two vectors if we multiply each one by a scalar? For example, if we double two vectors, their magnitudes and their addition doubles, but the direction remains the same. So, if we multiply two vectors by a scalar alpha, their addition is also multiplied by alpha. Now, suppose that we have two vectors a and b with the angle between them as theta. We can define their dot product as a dot b equals the multiplication of their magnitudes multiplied by the cosine of the angle between them. A dot b equals b dot a, and the result is a scalar. Dot product is distributive, meaning that the dot product of a vector with the addition of two vectors is equal to the addition of the dot products of them individually. As an example, if two vectors are perpendicular, the dot product is 0, or the dot product of vector with itself equals its magnitude squared. Let's consider an example. What is the dot product of this vector by itself? As you can see, we get this result, which is known as the law of cosines. Based on this law, if we have a triangle, we can write these formulas. Now it's time to define another operation called the cross product, which is the product of the magnitudes of the two vectors multiplied by the sine of the angle between them. Pay attention that this quantity is another vector in the direction of n. But in which direction? Suppose that a and b live on this plane. The direction of n is perpendicular to both these vectors and also to the whole plane and any other vectors living on that plane. We use the right-hand rule to find this direction. Put your right-hand fingers in the direction of A so that your palm faces B. Your thumb shows the direction of N. So, the direction of B cross A would be in the opposite direction. Cross product is distributive, but it's not commutative as I showed in the previous slide, because it has an opposite direction if we change the order. Geometrically speaking, the magnitude of the cross product is the area of a parallelogram formed by A and B. In a special case of 90 degrees, it is the area of a rectangle, and it is worth to note that the cross product of any vector with itself is 0. Now you might ask if cross product is associative or not. Suppose that A and B are equal and C is perpendicular to them. So B cross C is perpendicular to C, B, and A, and as a result, A cross B cross C is not 0. But suppose that we first find the cross product of A and B, which is 0, and then A cross B cross C yields 0. So these two expressions are not equal. Now it's time to define a vector in a different form. Suppose that we have these perpendicular unit vectors along the positive direction of x, y, and z. For each vector, we can find 3 components and define the vector in the component form. The magnitude of the vector can be calculated using this formula, adding the square of each component and taking its square root. We can do the same thing for another vector b, and using the component form of the vector, we can easily find the addition of two vectors. The unit vectors are perpendicular, so we can find the dot product of them with respect to one another. Using these dot products, we can find the dot product of any two vectors. It is worth mentioning that the magnitude of any vector is the square root of its dot product with itself. Now let's find the cross products. X, Y, and Z are perpendicular. Their cross products with themselves are 0. We can also use the right-hand rule to find the others. Take a look at them. Now let's compute the cross product of two vectors using their components. Take a look at these expressions. These three go to 0. And by finding the other 6 ones, we can finally calculate the cross product. We can rewrite the last line as a determinant in which the first row contains unit vectors, the second row contains the first vector, and the second vector goes into the third row. Now, suppose that we have these three vectors A, B, and C. How can we find the volume of the parallelepiped formed by these vectors? The area of the red part can be calculated using the magnitude of the cross product. We can also find H, which is perpendicular to the red plane, so it can be written as the dot product of A and B cross C divided by the magnitude of B cross C. By multiplying S and H, we have the volume, which can also be written as a determinant. Pay attention that we need the absolute value of the determinant. So if the determinant is negative, we just need to take its absolute value. Pay attention that if this value is 0, the volume is 0 and all these three vectors live on the same plane. Finally, it is worth mentioning the vector triple product, which can be measured using back-cap rule. Use the vector forms of the vectors in the parentheses and then multiply each by the dot product of the first vector with the other one and then subtract. As an example, pay attention that if we move the parentheses, the result would be different.